So good afternoon for everybody, but for Professor Sbpo, it's good night, good evening. First, I would like to introduce Professor Sbpo, and then she can start the plenary. It's a pleasure to announce the talk of Professor Sbpo from the Koç University in Istanbul, Turkey, entitled Representations of the Non-Dominated Set in Multi-Objective Optimization. Professor Sbpo has greatly contributed to the field of operations research, especially in the multi-criteria decision-making area and optimization. She served as a president of the Informed section of the MCDM community from 2018 to 2019. She also acted as a vice president in the previous terms, and since then she has been an officer of the board, and she's also in charge of the Junior Best Paper Award of the section. She has earned her bachelor degree in industrial engineering with a double major in mathematics at the Boğaziçi University in Istanbul. She also completed her PhD studies in the Department of Decision and Information Science at the University of Florida. And she then joined the Koç University College of Administrative Science and Economics, where she currently serves as a professor within the Operations and Information Systems group. Her current research interests are in multi-objective optimization, data mining, decision support, and healthcare. So, Professor Sbpo, I would like to thank you very much for accepting our invitation and to give this talk for our community, our Brazilian community in the Sbpo conference. So,
thank you. Thank you very much for this nice introduction, and thanks for inviting me. It's a pleasure for me to be with you today, and I am thrilled to join the 53rd episode of your symposium in operations research. So it has a long history, very, very nice. Thank you for this opportunity to share with you my research that I have spent some time on for a number of years now, for the last couple of decades, maybe, on and off. So I'll be talking about representations of the non-dominated set in multi-objective optimization. And this falls within my continuing area of research. Multi-objective optimization is an area where I started doing research during my PhD, and I indeed never stopped doing research in multi-objective optimization. So it's something that has always been there for me. Today I'll start by introducing the problem, and then I will talk about how we solve these problems, but in particular, the notion of representations. That is going to be the focus of my talk. And I will give high-level descriptions of two algorithms that I've been involved in developing, and we'll conclude with some remarks. I'll try to remember to check with you at certain points in case you have questions, clarification questions to ask. But if I kind of get going and forget stopping, feel free to raise a hand, and I'm sure other panelists can draw my attention. I'm not really that great in following chat, but I'll try. So the problem I'm going to talk about is a multi-objective optimization problem. It has P objective functions and one feasible set. The image of the feasible set under these P functions is itself a set. We call that the outcome set. It's the image of the feasible set in objective space. So that's another terminology that doesn't exist in single objective optimization, because when you have a single objective, everything maps into numbers and you don't have this multiplicity of dimensions in objective space. If your feasible set is also discrete, we call the problem multi-objective discrete optimization problem. Now, a quick reminder to everyone in OR community, I think this is well known, but just to remind ourselves that we are, of course, those of us who use mathematical programming, mathematical modeling, we are very accustomed to having one objective function and formulating everything else as constraints. But in real decision-making situations, there are indeed factors to be considered, not necessarily objectives and or constraints. And what's of importance is the trade-off among these factors in the real problem. For instance, if you think about portfolio selection, which one typically formulates imposing a budget constraint, the budget constraint may not really be a tight constraint. So depending on what type of return is possible, what the risks are, the decision maker may be willing to invest more. In another example, in radiotherapy planning, for instance, when they come up with a plan to bombard a tumor with radiation, which will also hurt the surrounding tissues that are trying to be secured, the trade-off again can be the levels of dosages of these X-rays can be formulated better if a multi-objective view of the problem is present. Of course, when you formulate a problem as a single objective problem, we also know you can always do sensitivity analysis and see what happens, for instance, if you have more money, less money in the portfolio selection problem, or in the radiotherapy example, if you allow more radiation, less radiation, and so on. But this is a local approach, which I am going to try to clarify in the next couple of slides, which misses the big picture. We are in multi-objective optimization interested in efficient and non-dominated solutions. This might be a familiar definition for you, also called Pareto optimal solutions. An efficient solution is a solution for which you cannot find any other feasible solution that is at least as good as this one. Our default is minimization in all objectives, and strictly better in at least one. If you cannot find something that is at least as good as this one in every objective, strictly better in one, we call this an efficient solution. The image of this is called a non-dominated solution. And we denote the non-dominated set as Yn. That's going to be the focus of my presentation, really. That's the focus of the field in recent years. The efficient solutions, of course, are of interest. They are the X's, the decision space vectors of the problem. So these are like your investment plans. But I'll be talking about the Y's, the images, the F values, what these lead to for the rest of the talk. Okay, so let me just tell you how we solve multi-objective optimization problems. You have P objectives. What does it mean to solve it? We are interested in efficient or non-dominated solutions because they have the trade-off information. How do you find them? We find them using scalarizations. On the slide, I have the 3 most common scalarizations that are used. Perhaps you might have used one of them in an application. Perhaps you are a researcher who investigates multi-objective optimization. The good thing about scalarizations is that if you solve this single objective problem, you are going to find a non-dominated solution. Any one of them will satisfy that property. The first one here is called weighted sum. Very simple. You just combine the objectives into a single objective by using weights, and then you optimize. And if you change these weights smartly, you can find all non-dominated solutions of convex problems. The second one, which I'll be using today, is called the epsilon constraint approach. You keep one of the objective functions as the objective function, and you convert the rest, the p-1 of them, into constraints with right-hand side values of epsilon. And then if, again, you change these epsilon values creatively, you find all non-dominated solutions of this problem. And there is a Chebyshev scalarization, which is also used, which has, again, a similar property, which I will not be talking about today. So what does it mean to solve this multi-objective optimization problem? In most applications, one solves a scalarized version of this problem. And if you think, for instance, all of your objectives are of equal importance, it is likely that you are going to add them up, and you will be finding a non-dominated solution, which is actually good. But sometimes this does not really yield a balanced solution as you might expect. By weighing them equally, you may not be finding the most balanced solution. Sometimes you might write the epsilon constraint formulation. Again, you say some of these objective functions are limited to these values. And again, that's going to find you a non-dominated solution, which is also good. But again, you cannot trust the solution all that well. Identifying the most preferred solution without generating the entire non-dominated set has been of interest historically. This requires interacting with the decision maker. This is a good idea, but the decision maker may not always be able to express their true preferences if they don't know the entire trade-off landscape. I'll be showing you some pictures shortly. So as a result, the vector optimization approach in multi-objective optimization claims that it is best to find the entire non-dominated set. This is the solution to the problem. And there has been work along this way. There are algorithms that use the weighted sum scalarization. So this is pretty much state of the art. There is this algorithm and the code, which is now called BenSolve, that relies on Benson's algorithm, who happens to be my PhD advisor. But the algorithm is by researchers Löhne and Weissing, this current implementation, and it is really very effective. We will solve linear problems for their extreme points and faces. The epsilon constraint approach has been implemented as well. My former PhD student and I contributed an algorithm for using this scalarization. The code for this is also available, and it works decently. And for the Chebyshev scalarization, the work comes relatively recently. There is the Holzman and Smith algorithm, which was not available with its computer implementation, but this enhanced version by Domingos Rios and others includes the Holzman and Smith version as well. So the code for this is also available. by the authors. So we do have tools to solve vector optimization problems, continuous ones and discrete ones. But there is also an issue. Now let's look at this continuous problem. This is a very small linear program with some constraints, 6 of them. And these 3 objectives are very simple, x1, x2, and x3 is being maximized so that the objective space and the decision space are the same here. And suppose you use bandsolve and you find the extreme points of this problem and you identify the faces. Bandsolve identifies the faces. Faces are these gray surfaces that you see in this picture. How do you present these to a decision maker? And how does a decision maker use this information to find and identify implemented solution? So one could present some discrete points selected from these faces for the decision maker to choose, like these orange points. Then they would have names attached to them, and the decision maker would evaluate and choose one of them. That would be one way to proceed. So this is very typical of continuous problems. Your non-dominated set is going to be of continuous nature. Even if you can compute it, it will be very difficult to convey that information to a decision maker. That is why we need a representation. And these orange dots are the representation here in this case. It's a discrete representation of a continuous problem. So if your original problem is a discrete one, you may still need representations. Here, this data comes from a 3-objective 100-item knapsack problem. It is, as a knapsack problem, relatively small, but this has more than 3,000 non-dominated solutions. So if you spend the effort and compute all of them, still presenting them to a decision maker is a lot of work on the decision maker to process, like 3,000 plus points to evaluate and choose the best one. Instead, one could think of selecting again a subset and presenting these to the decision maker. These orange points, again, I would call a representation. Finding representations of the non-dominated set has been a discussion that has gone on for many years. It goes back all the way to 1970s, really. One could find a representation relatively easily by solving a scalarization of their choice multiple times. You could solve the weighted sum scalarization with different values of lambda, the epsilon constraint scalarization with different values of epsilon. But how good would be the representation you obtain? That's the question. And there has been a verbal answer to this, starting from very early times, that says a good representation should not miss any big portions of the non-dominated set. So it should cover the non-dominated set well. It should not contain points that are very close to each other. And it should not be crowded. So you should not really throw thousands of points to a decision maker saying this is a representation. In an early paper, I tried to quantify these concepts, and I proposed one could attempt to do that by using these measures. The first one I proposed was I called coverage error of a representation y sub r. And again, this is easier to explain on the picture. The orange dots are the representation, so that is yr. And then you assume that any non-dominated point of the set, any point lying on a gray surface, is represented by a closest orange point. Closest using any metric of your choice. This could be the Euclidean distance, another norm that you like, whatever you find intuitive. But we interpret Euclidean distances quite well. So you pick the closest point to an arbitrary gray one, and that is the representer of that point. So the blue point I pick over here will be represented by the closest orange point. And the representation error, given these orange dots, will be the largest such error. In this case, that would be given by this triangle over here that is farthest away from the orange dots in the representation. So this is the worst represented part of the non-dominated set. So that distance is called the coverage error. So that was a proposal. And the second measure I proposed was called uniformity. This is really easy to understand. You have these orange points you're presenting as a representation, then the points in it should not get very close to each other. So you look at their point-to-point distances, and the uniformity is determined by the closest pair in the set. You want uniformity to be large, and you want coverage error to be small. And finally, the third measure was the cardinality of the set, cardinality of the orange dots, which is easy to interpret, so that's not going to be here. Now, the coverage error among the two, of course, is related to uniformity as well, but has been accepted quite well in the literature. So it has been used quite a bit. It is indeed a very pessimistic measure. So let me try to explain why I say that. Suppose that you knew the entire non-dominated set. So you would know all these gray surfaces somehow, and you know how to process them. And then suppose this green star is the decision maker's most preferred solution if everything were available. Now, let's suppose we don't know the gray set, the surfaces. We don't know how to present them, but instead we throw the orange dots to the decision maker and say, this is a representation, choose. And the decision maker, given this group, chooses this blue star over here. It's in the representation and she thinks this is good enough and is chosen. Now, the difference between the green star and the blue star is the actual error that happened because of the representation. If you had the entire set, you would have picked the green star. You didn't have it, you had the representation, you picked the blue star. The difference between the two is what you missed. The coverage error finds for you the worst case for this difference. So it actually assumes the worst and thinks that the most preferred solution could have come from here and computes the distance to a closest representative point as the coverage error for this representation. In that sense, it's very strict, it's very pessimistic. Okay, maybe I stop for a minute and see if there are any clarification questions that I should address. So shall I assume that everything is, the definitions are fine? Okay, so so maybe there's something.
I think that is fine.
Okay, thank you. So what I call representation algorithms are algorithms that look for these orange points. Okay, so instead of finding everything, every non-dominated point, some algorithms try to find a subset that I call a representation. There are quite a number of them. This is not a comprehensive list over here. There's a group of algorithms I call diversity maximizing approaches There is this landmark article by Silva and Crema in 2007, and that has many successors. I brought here only the relevant ones, striking computational results ones, but there are others as well. These papers have their own diversity measures, and they just have very reasonable, logical ways of navigating in the non-dominated set and finding a diverse set of elements. But they do not guarantee a quality measure. So at the end of the day, they do run computational experiments and their algorithms perform well, but when the algorithm stops, you actually don't know what the worst error that you are making could be. In the second group here, there are algorithms that guarantee a measure of quality, and some of them use coverage error. Some of them use something related that is called a representation error. But of course, they guarantee this quality without the entire set being computed. So I have an early paper here on a multi-objective linear program, given the efficient phases. And there is an article, a very good one by Borkrans and Forsgren, that applies to convex multi-objective optimization problems with any number of objectives. For the discrete case, multi-objective discrete optimization case, we have algorithms for p equals 2, the bi-objective case, and some attempts at p equals 3, but the general case has been quite difficult. So that has been missing for the most part. Now I'm going to quickly, at a very high level, go over two algorithms we proposed relatively recently. Between the two, this is the older one, and this was published in 2018. It is indeed a counterintuitive approach that uses bi-level programming to solve the multi-objective optimization problem. This is with my former student, Gökhan Kirlik, and the paper appeared in Math Programming in 2018. Now, if you are not familiar with bi-level programs, this requires some looking at. So this is quite challenging at first, but I'll try to explain what it does in on a picture, on a figure. So here, a bi-level program, as the name implies, has two levels. There's an upper level problem. You see this FU over here, that's the upper level problem, that tries to minimize the distance between the images of an X and the Z. Now, X comes from the feasible set, and its image falls into this set that we call S. S is a given closed set. Z comes from the feasible set. It's in the lower problem, okay? And the lower problem tries to minimize a weighted sum of objectives. And this Z tries to dominate X that's chosen by the upper level problem. So this is the structure of the subproblem we are looking at. This might be easier to understand what's going on with the subproblem. We have some X, doesn't matter what kind of an X we have, that maps into some Y, that doesn't matter either. We have a given set S, this square or rectangle. So the upper level problem picks an X, here labeled as X0, and the lower level problem, having a weight, the weights are given here, tries to outperform this X. And given this X0, the lower level problem would want to go to Z star because it's trying to maximize this W transpose F. The lower level problem would try to go as far away from this point as possible. But the upper level problem wants to minimize the distance between the X and the Z chosen by the lower level problem, the reaction point. Therefore, the upper level problem would actually prefer something that is non-dominated. So instead, for instance, if the upper level problem picks something on this dark line over here, which is the non-dominated set, this curve, the lower level problem would try to get away from it, would try to outperform it, but would fail. So the distance between the X and Z would be 0, which means the upper level problem achieves its best. And actually, that's what counts in bi-level optimization, the upper level optimal value. As some of you might guess from this picture with the yn plotted over here, if you solve this bi-level problem, the solution tells you, the result tells you things. Okay, so if you solve this problem, and if the upper level problem has an optimal value of 0, then you have a non-dominated solution that comes from this set S. That's what this tells you. If you solve this problem, and then the optimal value turns out to be positive, then you do not really have any non-dominated solutions in that S. Okay? Or this part is infeasible. The reverse is also true. So this is an if and only if statement. So the moral of the story is this bi-level problem helps you find, or if possible, find, if not, learn that there is none, non-dominated solution from a given set S. So in this picture, this very difficult to see blue rectangular prism here could be S, for instance. So the decision maker might say, let F1 be between 4 and 6, F2 be between 8 and 10, F3 be between this and that. So these might be given as specifications. And if you formulate this bi-level problem and solve it, the result is going to tell you something. It's either going to find a non-dominated point that comes from this set, or it's going to tell you there is no non-dominated point in this set. So one could envision that a mechanism to modify this set S could lead to an interactive approach that can actually find the most preferred solution of a decision maker. So that requires changing this prism, in this case, a rectangular set, and adjusting it based on the responses of the decision maker. Now, what we did instead was to say, what happens if we say the DM is not in the picture, the DM is not in the loop? Then we can use this idea to obtain a representation. The algorithm will get a coverage error requirement along with problem data, and then it is going to enclose the feasible region in a large enough set. And then it's going to start partitioning and solving this bi-level program for all partition elements. This will go on until the desired quality is reached. This is our representative set generation algorithm. And if you apply it to our toy problem, you can indeed find, without finding the entire set a priori. So you just give the problem data to this algorithm, and then you specify a coverage error requirement. And if your requirement is not high, you will get a sparse representation like this one on the right. If you are very demanding, and if your coverage error allowance is low, you're going to be get a crowded representation like the one on the left and top. As a byproduct, we also get an approximation for this problem that consists of boxes. That's due to the nature of the search strategy that we use here. And these are guaranteed to contain the non-dominated set. So we have for a continuous problem, this also gives us a way of expressing the faces to, in a more processable way. But still, there is one more step to add on to this to make this more interpretable to a decision maker, which we did not do. So going forward from here, there are a couple of things to be done. There's a lot to be done on the interactive front, but also improving the bi-level program solution is also possible. We didn't try to do that. We were just solving the bi-level programs in a very standard way, using a KKT reformulation and handling complementary slackness conditions by using binary variables, making the problem combinatorial. There can be better ways to do that. Their algorithm itself can be really adapted in different ways. There are different alternative partitions. We were using rectangles. There can be alternative partition elements to be used and so on. So this is a fruitful way to go forward, and especially the interactive use can be quite promising if there's a real application to attack. Now, let me take some time to talk about this other algorithm that we have been working on and off for many years. This is a representation algorithm for multi-objective discrete optimization. And it is based on an exact algorithm that we proposed years ago using the epsilon constraint scalarization. And starting from then, we have always wanted to adapt that to a version that finds representations instead of the entire non-dominated set. There has been quite a number of challenges, but I think we finally resolved all of them. Of course, we haven't been working on this for so many years nonstop, but things happen. So the paper now is almost done. So if anyone is interested, I should be able to email it to them maybe in due time, in a couple of weeks, if I'm optimistic. So this problem solves the discrete optimization problem with a representation approach. It gets the problem data and the coverage error requirement, and then it gives you representations that are guaranteed to meet the requirement without computing everything. So that's the idea. To give you the rationale behind this, let me briefly talk about the exact approach that finds every non-dominated point. Again, we are looking at a 3D problem with 3 objectives. The point you see are the non-dominated solutions. So the one that tries to find everything searches the epsilon space, the weight space that you see below on the floor of this 3-dimensional figure. We have F2 and F3 there. So F2 is less than or equal to something, F3 is less than or equal to something, and we want to minimize F1. That's the way the epsilon constraint approach works. And if you knew where the points were, of course, picking the epsilons would be very easy, but of course you don't know where the points are. So you are trying to search this flat 2-dimensional epsilon space. And in the meantime, find all of the non-dominated points by solving epsilon scalarization problems. Of course, this idea is not new. The theory has been there since 1970s. There has been a very commonly used algorithm for the bi-objective case since 1980s. And the generalization to P objectives has been challenging, but our contribution here has been formulating the search space management in a rigorous way and proposing a novel strategy that makes this computationally affordable, let's say. So this is the exact approach. And as you can imagine, from the beginning, we had this idea that, okay, this algorithm works for the exact case. It finds all non-dominated points. But what if we want to find the representation? Can we kill some of these rectangles earlier, instead of searching the entire space, the epsilon space? Can we actually navigate faster and do better? So that was the idea. And we solve here two-stage epsilon constraint problems. So reminding you what that scalarization looked like. Again, we have this problem pk. K is the objective that is picked to remain as an objective. The others are turned into constraints. And then we need a second level problem as a technicality to avoid weakly efficient solutions. And when we create this representation algorithm, a number of things happen. So going from the exact algorithm to the representation algorithm, first of all, we have to take the search space to RP. So we cannot live in a search space that's in the P minus one-dimensional space. Maybe I should more accurately say we couldn't live. Maybe it is possible to live in the P minus one-dimensional space. We didn't know how, so we had to take the search space to P dimensions. And then our original rectangle selection strategy, which was working well for the exact approach, didn't work well here. And we had to come up with an alternative rule for selecting the rectangle. And the rectangle elimination rule is indeed simple. You check the coverage error for the rectangle, and if the rectangle is already covered, you say, okay, there is no need to look into this further. Let's get rid of this. There might be non-dominated points in that rectangle, but we don't have to look because our coverage error requirement is met. So that's the logic. And our experience with this idea taught us a number of things. The rectangle processing order matters a lot. That's what we learned. The objective function that you pick in the epsilon scalarization matters a lot, which was not the case at all with the exact approach. The norm you choose to compute the coverage error, even that matters. So that was unexpected. If you choose the L1 norm, it is something. If you choose the L infinity norm, it is something else. And we experimented with these two norms mostly because they are linearizable. Even the way you normalize the norm matters. By normalizing, I mean adapting to problem data, using weights in the norm to scale things, scale objectives with respect to each other. Even that matters. Of course, problem size matters. Checking the coverage error is a very expensive task mathematically and computationally, and you could easily be worse off than using an exact approach. We address that by designing an upper bound. Instead of computing the coverage error exactly, we compute an upper bound on that, and that helped with that as well. A few words about what we were able to see, observe in this case. These are summary statistics from assignment problems we have solved, all three objective problems, 5x5 assignment problems, 2 50x50 assignment problems with 3 objectives. And here you see the y-axis shows the size of the representation. And you see, and with different levels of requirements for coverage error. The blue one refers to a very precise representation, and the gray one is quite a coarse representation. And you see these sets have like already, this 50x50 one has 3,000 points in the representation. That is way too much. but the original problem has 30,000 points. So these are really large problems, actually. A 50 by 50 assignment problem has a lot of variables. So this is really huge. And the representation is able to reduce the size to 10%. And even if you are very precise, and it can reduce it to 3% even if you relax that precision a little bit. So this is indeed the case with the CPU time. So you get half of the CPU time with reduction. That's also a good sign. When we look at the knapsack problems, again, we see a similar picture, halving CPU times. The set sizes, as you decrease the requirement, is stable. Maybe that's also a good thing because you're finding a lot of points with limited effort. So that's a positive thing. So in the end, we were happy with this, with the results that we observed with this representation algorithm. But something that is not on my slide, and I have to say that we say this in the paper, everything seems to work very well for the 3 objective case. It is a general algorithm you could apply to 4 objectives and beyond, but it already gets less beneficial as opposed to the exact approach when the number of objectives grows. So that seems to be the drawback. For 3 objectives, this seems to work quite well with good results, but going even further, maybe there is more to be done. To wrap this up, observing that multi-objective optimization is relevant in many areas of application, the representation approach proposes to rigorously seek a big picture of the non-dominated set by generating a sample of points with good properties. We know that if you have a lot of objective functions, more than 3, it becomes difficult to solve the problem without using some preference information obtained from the decision maker before solving the optimization problem. But for the decision maker, it is difficult to provide the preference information without knowing what's going on with the problem, without having a good understanding of the big picture. The representation algorithms are designed to address that, provide the big picture in a computationally manageable way and a theoretically justified way. So with measures of quality, with error bounds saying that the worst case error in the set is bounded by this value. There is very much work that can be done in representations. There is algorithmic work to be done for sure. Definitely the algorithms that are there can be improved. We should be searching for lower cost, higher quality representations. So definitely worthwhile. And there's theoretical work to be done. And there, I think the most important is searching for new measures of quality, because the ones that we have, coverage error, which is really well accepted, is making things expensive. So maybe there can be measures like our upper bound was helping a little bit in this algorithm, but maybe there are measures that can be better and could be embedded in algorithms. So that's definitely an area for future research. And of course, it would be great to apply these to applications that I would love to see or be part of to apply these ideas in a real setting and see them in action and address the challenges that occur in action, because I'm sure there'll be more challenges than my algorithmic work in a real setting. Okay, so I think that's all I have planned to say. I'm glad to answer any questions you might have, and thanks for listening. And
okay, Sbpo, Professor Sbpo, thank you very much for your presentation. Very interesting case.
Thank you so much, Dr. Mota. Thank you.
So we have time for some questions. Let me open. You can also write a question in the, you can write in the chat. The point is the people cannot
they cannot unmute themselves?
No, they cannot talk, but they can write a question in the chat, and if it's necessary, we can open. That's why it's a little bit difficult for this interaction. You see?
Yes, I see one.
Yes, there is a question. Yeah.
It's in Q&A, not in chat.
Yes, in the Q&A, yes.
Okay, so by using the representation, the decision maker chooses the optimal solution, or we could use it in order to define our parameters, such as the epsilon. The idea is that by using the representation, the decision maker chooses the optimal solution. So that's indeed the intention. You create the representation in a good way, in a guaranteed way, and then the decision maker chooses the one that seems to be the best. Yeah, that is the intention.
Right.
I hope that answers the question. I'm not familiar with this Q&A environment, so it's I think this webinar format.
But
okay. There is also a question.
We have also the option to open the audio of the participant who may want to make a question.
Okay, there's another question in chat. If the decision maker's preferences are known a priori, how are these preferences to be obtained? That's a very good question. That's not my area of expertise, but you might have presentations in your symposium that address that. So we have experts in your community who focus on that. That's not my expertise. You ask questions to a decision maker to get these preferences. You typically ask comparison. I think that's most popular lately. You ask comparison questions. So you obtain interim solutions and you ask the decision maker to compare them. And based on the responses, you have a mechanism that tells you which way your search should go, whether you should be trying to increase an objective, decrease another one, and so on. But that's very difficult. So in general, to obtain the preference information from a decision maker, and of course you cannot ask 1,000 questions, so it has to be limited interaction. And that's why those of us who promote representations, we think this is better in that sense, because you don't have to have the decision maker in the loop. And eventually the decision maker will have to choose, but at least they don't try to answer preference questions. But very valid question, how to obtain the preferences.
Great.
To have a big picture of reality, how could we define the set of attributes and how it can turn the algorithm complex? Yeah.
It's a hard question.
Very difficult question. If you, it depends on the problem dynamics, really, and it depends on how precise you are trying to solve it. So I do not have too much experience on applied problems, but I did work on, for instance, on this radiotherapy planning optimization problem. We used maybe like 7 objective functions, and they were ugly objective functions. There were like risk measures, standard deviations, and dosages received, not received, and so on. And it does make the algorithm very complex. So if you try to bring in more elements, if you add more objectives, it becomes a better representation of reality, but then it becomes difficult to solve. There's a trade-off there as well. And then, of course, if what we did in our application, which we had to solve, maybe I should say that, we ignored the quality guarantees. So if you give up the quality guarantee, you can actually solve, and we trust that they are good solutions, and they were received well by the physicians. But mathematically, we were not able to prove that the errors are bounded. So this is like a heuristic approach, I would say. It makes the algorithm complex if you try to provide error bounds, but if you have a heuristic approach, you can solve pretty big and complex problems. Yeah. I hope that answers the question.
I think that's yes.
Oh, are we out of time?
No, well, we still have time for some questions, but I just I have one. Most of the questions were about some kind of interactions with the decision maker. We know, as you said, that your objective was to reduce the non-dominated set. And this is quite interesting for making the problems easier, and then to try to explore those solutions. But have you think of how this interaction with the decision makers could help finding a better representation? So the point is, you try to make a representation without the information of the decision maker, but if you have any kind of preference information, I hope that you could find a better representation just to try to interact with the decision maker and to try to find a good solution, a compromise solution.
That's a very good point. So this is indeed something I would like to do very much. And I indeed thought about it a bit, but never got to implement it. I think the one thing I would want to try, I don't know if that would work, but in a real setting, is to first come up with a very quick and coarse representation, nothing refined. And then get the decision maker's feedback and try to figure out which point seems to be attractive. So among the limited set, what does she like? And then focus on that part of around that point, I should say. So the decision maker, you give, let's say, 20 solutions and picks one. And then you try to now cover the neighborhood of that solution. But when I say neighborhood, kind of a relatively large neighborhood. And then again, present some solutions. So instead of finding everything a priori, then you find this local representation and then get feedback again. But I do not know how this would work, because you have to experiment with this decision, in a real decision situation. How many iterations can you make? How easy would that be to pick the point and give the feedback? That I guess relates to this question on chat about preference learning as well. I think there is a potential to the way I described, to try to learn the preferences of the decision maker, but that would require building. I think the key there is the navigation strategy. So I'm pretty sure you start with a rough representation, get some feedback, but what do you do next? That will require some thinking.
Yeah, and also when you do that, you can introduce some bias. Yes, like as you said, you could try to get that information and search in local, but if that information is not really precise, also you can be biased at that neighborhood, at that location. So I think it is still quite challenging. Yeah,
that's another challenge. Of course, that's the pitfall that we want to avoid. You don't want to be locally trapped. So that's something to be careful about. So how to maintain the global look, but also try to focus on the region that you like. So that requires some challenging balancing act, I guess.
Yeah,
that's future research if anyone is interested in pursuing that. But I think that would be really interesting if one had the right setting to experiment with. This I think hypothetically is not as exciting to do. So if you have a real decision situation where this can be experimented on, it would be great.
Yeah. Okay, let's see. I think, well, we don't have any Q&A questions. So Professor Sbpo, thank you very much for your presentation, for your very interesting topic, for sharing your knowledge with us. And thank you because you are now in your time to rest. And you and you are here with us.
Well,
although you are very, very far, but this is a good thing of having a virtual conference.
Right. Thank you very much for listening and for these very, very nice questions. So I really enjoyed being with you and hearing your feedback. The pleasure is all mine. So thank you so much. And the time difference is there, but that's, well, and I'm sure you are in a very nice climate, in a very nice place. So that is also attractive. It would have been nice to be there physically, but this is also easy, and it's good to have technology make this possible. Really, I get out of class and then in a couple of hours I can be with you. So that I think is amazing. So thank you very much for inviting me, for having me. So I enjoyed it very much.
It was an honor to have you as
thank you.
One of our plenary. Thank you very much.
Thank you, Caroline. So,
okay, bye.
I guess that means bye, right? So yeah. Yes, I saw some talks in English. I couldn't attend today because it was my teaching day, but I guess I can attend some maybe.
Yes, you can attend. Yes,
tomorrow, and I'll have.
You are very welcome.
Maybe I'll see you around.
Yes, I hope so. Yes, most of our sections is in Portuguese because this is our like a national
it would
event.
Be the same for us.
But we always have plenaries from people around the world, and some sections are in English when we have people from abroad. But
I did see some technical sessions with papers in English. So I am assuming the talks will be in English too.
well,
No,
not necessarily.
not necessarily.
But we will have to a section with the best paper, an award, and the presentation is in English in that case.
Okay.
For the best paper.
Okay.
So you can join that one.
Yeah. Yeah. Thanks so much.
Thank you very much.
Bye-bye.
Bye-bye.